Okay, we're back from the break. Okay, this is just a little bit more of the evolution of electronics and transistor technologies. It comes from Intel, and it's sort of a summary of what happened from 1940 onwards. Here's a photograph of the first transistor that was built at Bell Laboratories, and this is another picture of it. And this is an example of where a transistor was used in a hearing aid, and then a first transistor radio. The other thing to point out here is that Julius Edgar Lilienfeld filed a patent for a field effect transistor in approximately 1925, and this is one of the figures from it, and it definitely looks much more like a field effect transistor than certainly these other devices on here. The other interesting point about Julius Edgar Lilienfeld is his advisor was Max Planck. Anyway, here's a few other things that I'd just like to point out. I guess in around the late 50s, Sony would introduce the television. In 65, Moore states Moore's Law. In 1971, a microprocessor was launched. It's the 4004, and it's shown over here on the right. And basically, you can see it's a bit of a rat's nest, and it looks like it was primarily routed manually. Here's a picture of someone in a clean room, sort of some of the early devices that the transistors showed up in. It's sort of a calculating machine of some type. And then an example down here of the 8080 processor, which is a precursor to many of the early processors used in home computers. In 1981, Intel introduced the 8088. Here it's shown over here, and you can see it's getting much more structured. And I think in 1982, they introduced an improved version of that, the 8286, which had 134,000 transistors. This is around 1979-1980, a PDP-11 LSI processor that stood for large-scale integration, and this is what we used to program an assembly language in fourth-year ECE, and we were actually pretty happy to do so. Just to put things in perspective, within 6 years of release, I guess 15 million 286-based personal computers were installed, but there's something that I pulled off the web a little while back. The Galaxy S2 has sold 20 million in 10 months since April 2011. So it puts things in perspective how quickly electronics can proliferate. In 1983, the first cell phone was, made available to the public. Cost roughly $4,000, so approximately the price of 6 iPhones. And it would have been an analog device, but it was transistor powered. With the creation of the World Wide Web, of course, that was a really big technology driver for electronics, and certainly has been ever since. The 1990s, here's a quote from Austin Powers. You're not missing anything. Believe me, I've looked into it. There's a gas shortage and a flock of seagulls. That's it. I guess most of you were born then. One of the things to point out here, around 2005, a dual-core technology introduced. And one of the things that also improved the processing technology is this high K metal gate, and we'll look a little bit into that a little bit later. Typically, this meant that the dielectric constant was higher than that of typical silicon dioxide as an insulator, allowed you to put more charge into the channel. And just to bring things a little more up to date, there's an i7 with 731 million transistors, and it should be obvious that that's a quad core. A little bit of the processor evolution. This sort of shows the technology that they were built in and sort of the speeds that they ran at and the number of transistors. So this is that early 4004 that I talked about before. It was a 10 micron process. It wouldn't have been CMOS, I don't imagine. The Intel 8008, which would have been a descendant, I guess, of the 4004. This probably was 8-bit. Maybe this went to 16-bit. Don't know for sure. Number of transistors certainly went up, and the clock speed went up, and the technology stayed the same. So it would probably be a much bigger chip. The Intel 88, introduced in 74, initial clock speed around 2 megahertz, 4,500 transistors in a 6 micron technology. That probably was also not CMOS. In around 78, the 8086 processor, 5 megahertz and 30,000 transistors, and that would have built in a 3 micron technology process. So I guess this was the first 16-bit processor delivered 10 times the performance of all its predecessors, it says. Moving right along, let's say the 8286 up to 6 megahertz, 134,000 transistors. Pointed out before, the technology went down, 1.5 micron technology. Moving along again to a 386, speed went way up again, 16 megahertz, 275,000 transistors. Technology staying the same. And then let's say until 486, 25 megahertz, and a 1 micron process. And many more transistors. So that's sort of Moore's law at the processor scale. Here again, you can sort of see some examples of a Pentium Pro, 5.5 million transistors, 200 megahertz clock speed, in a 0.6 micron technology. So that's still pretty dated by our standards. Here's an example of a Intel Pentium processor introduced in 2002 with a clock speed up 1.7 gigahertz, getting way up there, 55 million transistors in what's called a 90 nanometer node technology. When I talk about technology node, it sort of refers to the size at which you can build a device, and it could be related to the pitch of the lowest level metal lines, and make a nice assignment to go try to look that up and see if you can find a nice concise definition for that. Here, 220 million transistors. Here's speed going up to 3.2 gigahertz, 65 nanometer technology. Some other ones to point out here. Let's say the Intel dual core, 1.66 gigahertz, but it's 1.7 billion transistors in a 90 nanometer technology. Here's a quad core. Number of transistors sort of went up 4 times from that, and the speed also went up as well, and the technology shrunk. I'll just point out a couple more here. Let's see, here's a quad core, 820 million transistors in a 45 nanometer technology, operating greater than 3 gigahertz when it's released. Just to bring things up to date here, we're more or less in this manufacturing realm of 28 nanometer technology node for modern CPUs and FPGAs such as Altera and Xilinx, and that was in around 2011. Here's some of the major vendors for transistors and microelectronics. Some of them you recognize, and some of the drivers you'd be familiar with. So, not unsurprisingly, Intel, number one, Samsung way up there, Texas Instruments, Toshiba, some of the others less familiar, Qualcomm. This is a company that's sort of pushing the 4G and LTE mobile services. It's sort of one of the big pushes of the CDMA early on. The STM Microelectronics, a big provider of ARM core devices, as well as a bunch of other things. One of the things you'll note on here is that there's no FPGA vendors in here. If you included all FPGAs all in, you're approximately 10% of the market, which is still a lot, but certainly wouldn't make it into the top 10. Here's some of the breakthroughs. This is an IBM slide, so some are related to breakthroughs at IBM and consortium companies. Some you'll recognize, some are a little bit more obvious than others, and I'll only point out the ones that seem relatively obvious. Moving the interconnect to copper. In the early days it was aluminum. Moving to copper made devices a lot faster because copper is a much better conductor than aluminum would have been. And there were some material challenges to basically deposit copper in terms of an integrated circuit. A lot had to do with the fact that it oxidized more heavily than aluminum, and probably wasn't compatible with other materials that we're using at the time. Obviously, big architecture improvements. Going to a dual core, you can put many more devices on your chip if you just replicate something. Some of the device or materials level improvements were this high K dielectric, which basically replaced the oxide layer with something with a permittivity greater than that of a silicon dioxide. Some of the system integration improvements are 3D chip stacking, where you basically try to stack individual chips or try to basically build vias through chips so you can interconnect chips more closely. And then the EDRAM, which just means embedded DRAM. The challenges there would be to make a DRAM process compatible with your standard CMOS process that you're using to make your CPU in the first place. And here's some that I put that are most recent. This is what we sort of think of when we think of our planar FET, and much of the technology when you're in the deep submicron has gone to this FinFET technology, where basically it's this device over here, but it looks more like a fin. And we'll look at this in a fair bit more detail, because one of the things that happens when you go to this FinFET is you have the parameters that you can choose to enhance the performance of the device are somewhat limited here compared to here. For example, you can make the device as wide as you like to give it more drive, but you really can't make the device in a fin fit any wider than it's shown there. So you typically have to use multiple fins. This is just a slide from IBM that sort of pointed out the advances in going to a 32 nanometer process, which was the high K, so the high permittivity and a metal gate, and they had a 35% performance boost and a lot less power. And you can look at the companies that were involved here. These are all the major players, some of the major players that we saw from this slide a few back. Here's an example of a GPU. This is, of course, a card with a GPU chip in it somewhere. And this sort of looks at the transistor count and the different families of GPU devices that were built by NVIDIA. And here it shows the technology that was built in 65 nanometers down to 40 nanometers. And here's a quote from people at NVIDIA. I just pulled it off the web somewhere. And it said, I asked two people at NVIDIA why Fermi is late. And NVIDIA's VP of market production basically indicated that building GPUs that big is very hard. Anyway, we'll take another little break here. Up to this point, we discussed the course in very broad strokes, started some discussion as to technology and related issues with making transistors smaller and smaller, and just a little bit more terminology, so everyone sort of is speaking the same language. So next, a little bit more of the same and an MOS refresher.